So finally, we've come to the last section of the course, which is applied optimization. This is section 4.7. Applied optimization. This section here is not really about a new material or new concepts, just like the one before, 4.6. But it's just apply, as the name of the section suggests, is just an application of calculus techniques and tools that we've developed throughout the whole semester. And in fact, I mean, most of these applications, or at least some of these applications, were behind the original motivation for the development of the theory. In the beginning, people wanted to find out, find out a way of tackling problems that involve finding an optimal shape, um, an optimal production level. So all things that were highly motivated by real world problems. And the development of this technique was it proved not only applicable to the original problems that they were attempting to solve, but it proved very useful in many other contexts as well. Of course, it also applied to infinite dimensional problems, which is nothing like what we're going to see here. But the analogy was there, and so this has led to the fruitful development of new theories, inspired by this infinitesimal calculus and its considerations in general, and the ideas behind everything. So what is a typical kind of problem that we have? So we are given a geometric, physical, or most applications that we're interested in for this course, we're given a problem or an economics problem, whatever, and then we are asked based on this word problem to find an optimal shape, a way of arranging things that leads to a minimum cost, minimum length, maximal area, and whatnot. So the challenges here are slightly different from other problems in math in this very same course. So the first thing we'll need to do is to write an objective function, and then find a min or max according to what you're asked to do. This is not always possible. Remember that when we look at optimization from a purely mathematical point of view, we stumbled upon cases, for instance, when the function was not continuous, or where the function was defined over an open interval, where we wouldn't have maximum or minimum. Okay, so this is not always going to be possible. We'll learn how to identify or how to treat cases where the tools have to be adapted a little bit. But this comes from the calculus. It comes from the calculus tools. So once you find a function, write down, identify the objective function. So this is to here for the first step, you need to extract from the problem what is f, and then what is the interval, the interval a or interval I over which f is defined So once you're able to do that and extract that information from the problem, then the rest is just going to be a matter of applying the techniques that we learned in the previous sections. So just to find the critical points, look at the endpoints, and see which one is better and all of that. So once I mean, the first part, then you would we might think of it as transforming the problem into a mathematical problem. Once you do that, so once you find you write the problem as a problem of maximizing or minimizing the function f over an interval, then everything, I mean, then now calculus will take over, and you just need to apply what you already know. Okay, so we'll need to recall a few of the steps that go into finding the minima or extrema. So the steps for finding extrema. So we need to find the critical points of f in AB. Remember that the interval may be AB closed, AB open, semi-open, whatnot, but we look for the critical points in the interval AB. This is usually not given to you. You must interpret. I mean, you must get that information from the wording of the problem. Whereas, I mean, for instance, there are some quantities that cannot be negative, such as length and stuff like that. And so the function can be defined only for positive values of the variable x. So that's what you need to extract that from the wording problem. So a b and the interval over which f is defined, you need to find out. But no matter what, they need to find the critical points of f inside the interval. So in the open interval AB. Then we need to evaluate f at the critical points and also at the endpoints. Okay, so we need to record those values to compare them in the end, which is the third step. So among the values found in 2, we need to identify the largest and smallest value. Okay, one thing that we need to remember here is the fact that critical points are not only points where f prime is equal to 0. This turns out to be the case when your function is a polynomial, for instance, or a cosine or sine or an exponential, but it's not always the case. I mean, there are some functions you will be given that will not be differentiable at a point. So when f prime doesn't exist, then that is also a critical point. Now, what is so there are some examples you may have seen before where you're asked to find an optimal shape of a geometric object, and some that look very intuitive. We're just gonna take a look at some of these examples Again, now after the development of all the tools that we have, we're gonna try to formalize everything to make it a method that can be applied to any such problem. Okay, so we'll start with something you most surely have been asked or asked yourself in the past, and you can guess the answer more or less right away based on your intuition. So this is this is kind of the first application that people think about when we think about applying optimization. So a piece of wire, yeah, so a piece of wire of fixed length. I mean, it's just you cannot stretch it or compress it. Length L is bent into the shape of a rectangle. So which dimensions produce the rectangle of maximum area? Okay, so we start with a wire of length L, and well, I mean, this is not going to be very precise, but so we turn it into a rectangle like this. So we turn it into a rectangle. So the perimeter of the rectangle will be fixed, and it will be equal to L. So one of the reasons to go through this example first is because it highlights the importance of all the points I was making at the beginning. So one of them is to identify the function f that we need to maximize, but most importantly is to identify the interval. Okay, so here what is, and just from symmetric considerations, you can immediately guess that the maximum will achieve when this is a square. Why is that? Because if you let this quantity here be very small, then the area will tend to 0. And if you try to make it larger, at some point this side here will be very small, and then again the area will become very close to 0. So the point in between is when the both sides have the same length. I mean, they have the same length, and that corresponds to a square. But we are here not interested in the actual answer, but how to get it in a way that could be transformed into a method. So let's give ourselves some variables here. So we're going to call this side x. If this side is x, that means that the other side is also x. And if this side is y, well, we know that the total perimeter is L. Okay, so we're going to give ourselves the variable x. But y is completely determined by x, because we know 2x plus 2y must be equal to L. So that implies that y is equal to L minus 2x over 2. Remember, the perimeter must correspond to the total length of the wire. So now the area, what is the area? The area is x times y. But we want a function of only one variable, and y is completely determined by x. So this is just x times L minus 2x over 2. And this is what we want to maximize. So this is the function f. So we want to maximize a of x equals x times L minus 2x over 2. Alright, so this is the function f. This is the first thing we need to know here. Next, we need to identify the interval. So where is a? Where are we going to? Where are we maximizing a? That's the question. So, as we said before, x has to be greater than 0. It's a length. So here x cannot be negative, right? So x has to be greater than 0. Now, what is the maximum possible value of x? That happens when y is equal to 0. So y has also, y needs to be greater than or equal to 0 as well. And this condition here implies that L minus 2x over 2, oh, this is wrong over here, it's L minus 2x, all that over 2. This has to be greater than or equal to 0, right? So both x and y have to be positive. This one prescribes a lower bound on x, and this one prescribes an upper bound, upper limit on how big x can be. This implies that L is greater than or equal to 2x, or what is equivalent, x is less than or equal to L over 2. Okay, so that putting this together with the other box, we realize that the interval here, so x is in between 0 and L over 2. So the interval I is 0, comma, L over 2. So we have everything now. We have the function a that we need to maximize, and we have the interval I. The rest is just applying what we already know from previous sections. So now we turn to optimizing to the optimization problem. Optimization to the optimization problem. Okay, so the first step, so what are the critical points? A of x is smooth, so it's differentiable, and many times, it's infinitely many times differentiable. It's a quadratic expression, so okay, let's write it this way. So first we find the critical points. Critical points are only points where a prime is equal to 0. Alright, and because the derivative of a is defined everywhere. So what is this? So if we can apply the product rule, or simply expand this into that, so we get x times L over 2 minus x squared minus 2 x squared over 2, which is just x squared. So a prime of x is equal to this expression here, prime, and that gives us L over 2 minus 2x, and we set this equal to 0. This will only hold if L over 2 minus 2x is equal to 0, which implies that an x is equal to L over 4. Okay, so what is A at the endpoints? At the endpoint of the interval, A of 0 is actually 0. You're multiplying 0 times L over 2. And this is the same as A at L over 2. This is symmetric. Okay, if you plug this in here, you see that at L over 2, this is 0. And at 0, this factor here is 0. So it's 0 both endpoints. And, well, it's not surprising, I mean, then that the maximum is achieved at L over 4 at the critical point, so at L over 4, A of L over 4 is equal to, well, we'll substitute that into A of x. L over 4 times L minus 2 times L over 4, all of that divided by 2, and this is equal to L over 4 times L over 2 divided by 2, then becomes L over 4 squared, or if you want, L squared over 16. Which again, well, this is a positive number, so this is a positive number, so then it's clearly greater than what happens at the endpoints. Okay, so conclusion, the optimal shape, meaning the one that maximizes the area, corresponds to a square of size L over 4, and for the area then, and area L squared over 16. Okay, that's it for now. So this is the introduction to the apply optimization section, and in the next module we'll more into that. We'll look at more complicated examples where perhaps we're trying to maximize or minimize quantities over not necessarily closed intervals. So that will change things a little bit, but we've already seen how to handle that from the mathematical point of view in previous sections. Okay, but we'll remind you about all these things in the next module. See you then.